Good morning. Am I audible? And can you see the presentation? Okay, fine. So we start with our unit number 3, that is process synchronization. So our outline for this unit is we'll go with few background for understand the critical section problem. Okay. So then we'll proceed with critical section problem. What are the expected attributes of solution? Solution. Then we see why hardware is required. Then different type locks like mix locks and solution provided by operating system in terms of semaphores. And then we'll discuss few classical problems of synchronization. Then the limitations of what is necessary monitors. That is the outcome for this unit. So let us start discussion with a simple background for it. We discussed about the currency, right? So meaning of that is processes can execute concurrently. If we have multiple processors, yeah, we can say they are executing simultaneously at a time. But still the meaning of concurrently is like the operating system deal with the state of process. So like one process is in running, may be executed for some amount of time and then maybe interrupted. Okay. For many reasons we already discussed. And this partial possible, and whenever again that process is scheduled, it will continue from where it was interrupted. Right. So very first thing is processes can execute concurrently. And while we have multiple processes for execution, we have already discussed about the relationship amongst the processes. If they are working on the same problem, we call them as a cooperating processes. And if they are altogether working on something different kind of problems, then maybe there is a competition and competition in terms of acquiring the processor. Okay. So every process tend to be finish their assigned work. But whenever cooperating processes are there, the most important aspect of cooperating process is something called as a shared data. Let me select this one. Shared data means, or maybe some sort of a data, think of like a global data, or maybe we have shared memory segment, or maybe any way by which more than one process. And of course, for this unit, you can think of process and thread in the similar way. Okay, so you can use these words interchangeably, no problem. So why I mentioned this is the same problem lies with threads also. And if we want to write quick examples, as we already aware, threads share the data, it is possible to produce this kind of errors very very quickly. Okay, so whenever concurrent access is allowed to shared data, it may not that there are chances of data inconsistency. Data inconsistency. Anyways, we are going to see one example on this. So the important part, concurrency, processes are running concurrently, and if they are sharing data, it may result in data inconsistency. So two important statements. Now, in order to maintain the data consistency, we should have some sort of mechanism which will ensure the proper execution of cooperating processes. Now, see why this is required again, because if simultaneous access results in data inconsistency, then that definitely creates a problem, and then system is of no use. And that is the reason we need to provide some sort of mechanism. And this mechanism is synchronization. Okay. So we need to provide some sort of mechanism so that we ensure the consistency of data, irrespective of any number of processes simultaneously accessing the same shared data. Okay. So this unit is all about this mechanism of synchronization. And to illustrate the problem of data inconsistency, so one example is mentioned here. Fine. So we have already discussed one of the classical problem of interprocess synchronization, and that is producer-consumer problem. We have just discussed what the problem is. We already aware what are the producers doing, what are the consumers doing. Okay. Now a smaller extension of the same problem is mentioned here to just illustrate the problem of inconsistency. Suppose we want to provide some sort of solution to our producer consumer problem. Okay, that fills all the buffer. Now here, because I mentioned about all the buffer, it is bounded buffer producer consumer. Meaning of that is bounded is what? Bounded is limited. It is bound by its upper limit. So we have a bounded buffer producer consumer. So some sort of capacity is there, right? Now, how we can provide this the solution to whether we want to check if there is any free buffer or not. And one simple solution is by making use of counter. So idea is very very simple. For example, suppose the capacity of my buffer is, let's assume it is n, or for simplicity let us assume it is 5. Whenever one item is produced by producer, what producer will do is it will increment the counter. Okay, and later everybody will simply check what is the value of this counter. If it is equal to full, that means buffer is full. As simple as like that. So this counter will track the number of elements in the buffer. It's very simple thing. So for example, next turn is of another producer. It will check the value of the counter, which is 1, which is less than 5, because 5 is our capacity. It can produce one more item. Whenever it is turn of consumer will see the value of counter is equal to 2. That means two items are available there. So one of the item will be picked by the consumer, and because one item is removed, it will decrement the counter. So it is very simple. We have a shared variable called as counter, which is initialized to 0. That is the initial stage, and it will be incremented by the producer whenever new item is produced and put into the buffer, and this will be decremented by the consumer whenever it consumes the element from the buffer. And now that can be utilized for kind of a synchronization. How synchronization? So for example, if the value of counter is equal to 0, we can stop the consumer because there is no item to consume. If the value of this counter is equal to n is, say, for example, capacity, let us assume 5, then we'll stop execution of producer because there is no space to store the produced item. So we are synchronizing between producers and consumers. Okay, this is what the logical solution to check how many elements are there in the buffer. If it is 0, stop the consumer because there is nothing to consume. If it is equal to capacity, stop the producer because there is no space to store this new item. Now, even though it is logical, now right now, as I mentioned, two operations on this counter, one is increment and one is decrement. Okay, and increment could be happen concurrently because we have, it's not like there is a single producer and single consumer. No, we may have multiple producers and multiple consumers. So this increment operation can happen simultaneously. Decrement operation can happen simultaneously or concurrently, or increment and decrement, like producers, mix of producers and consumer, that happens concurrently. Okay, and this concurrent access results in data inconsistency. How? Let us see on the next slide. For example, now whatever the dimension, suppose this is the infinite loop of a producer, where what producer does is assume that there is some sort of logic here which will produce the item. Okay, this is kind of a synchronization. If the value of counter equal to buffer size, that is what I mentioned, is equal to capacity, do nothing. Try to understand this. Semicolon immediately after this while. Meaning of this is what? Do nothing. It will be in the loop only. Okay. If it is not equal to buffer size, yes, there is space. So whatever the item you produced here, so at step number 1, so that element will be stored into the buffer. So this in index represents whenever we want to store the data into the buffer. And now we just want to modify this index. Now this is kind of a circular queue, so we want to modify index with in is equal to in plus 1 mod buffer size. And now because one element is stored into the buffer, we just want to increment the counter, something like this. So the logic of producer process is very simple. Step number 1, produce the element. Step number 2, check if there is a space. If no, wait. If yes, there is a space, put that element into the buffer, modify index so that next element will be placed at proper place, and increment the counter because we just put one and we stored it into the buffer. So 5 steps, and this can be executed by multiple producers also. On the same line, the of consumer is also mentioned here. While true, that means again it is the infinite loop. While counter is nothing, So nothing is there here. And meaning of this is if the value of counter is equal to 0, that means yet producer has not produced any item. So consumer cannot consume anything. Excuse me. Okay. So if the value of counter is equal to 0, that means producer is not produced anything. So it has to do nothing there till the value of counter greater than from 0. Otherwise, yes, there are items available. So now take the item from buffer. Previously, it was exactly reverse. Buffer of in was on the left hand side of assignment. Here it is on right hand side. So take the item from the buffer, and out index is used for that. I think I already mentioned this part. It's like a circular queue where the rear end and front end is there. Here just indices named as in and out. That's it. So this is modified because of again the nature is circular, and this part is important. Counter minus minus. So counter minus minus means because already some elements are there, I just picked up one element from the buffer, so I just want to reduce it. So that is what the logical solutions for producer and consumer, where this counter part is shared between the producer and the consumer, right? Now this is the most important thing. Even though we are saying counter plus plus, you can imagine that as a C language statement, right? Counter plus plus. But how it is implemented in machine language? Typically, whenever we have load store kind of architecture, so whenever we say counter plus plus, how it is implemented, see, counter is just a variable, right? And variable denotes the memory location. Okay, so this is kind of a load kind of a thing, wherein the value of counter, that is the value at this address, will be loaded into your accumulator. Let us call that as a register 1. Then value of register 1 is modified by something like this. Register 1 is equal to 1 plus 1. Okay. Now this changes the second statement where we modified the value of the register or say accumulator of your processor. So here we loaded the value into the accumulator or in the register. Here we modified, and this modified value is again stored back to the memory location. So this is memory location, this counter is memory location, this is counter memory location. And exactly similarly, this counter minus minus is also implemented. Only thing is here operation is action. Okay, and again you can imagine of like maybe register 1 or 2, doesn't matter actually, right? Now this is how the plus plus and minus minus operations have been implemented. Any doubt in this? Do you have any doubt in this? Because whenever we say counter plus plus in C like language, actually if you see the machine code for that, if you already studied something like store, load, add immediate, something like that, 885 or 886 instructions. Okay, so those are the actual instructions used by the processor. Fine. So even though counter plus plus is the statement in higher level language, three machine instructions are required for that. There are three machine instructions. Similar is the case for counter minus minus, right? Now with this background of how they could be implemented, let us have a look at something like this. Now let me tell you what is this. Assume that we have the value of count equal to 5, okay, and then one round of producer and one round of consumer. That means counter plus plus and counter minus minus. Producer, what producer does is counter plus plus, and what consumer does is counter minus minus. So this counter plus plus results in three machine level instructions. Counter minus minus results in three machine level instructions. So 3 plus 3, 3 plus 3, that gives me 6, right? And as I mentioned, the producer is separate processor and consumer is separate processor thread. We never know the order of execution. Why? Because that will be decided by the scheduler, right? So let us assume that this statement number 0, F0, statement number 0, where producer was selected by the scheduler, and one of the statement in producer was counter plus plus, and that counter plus plus actually needs three instructions, or out of that this is the first. So register 1 is equal to counter, where counter denotes the address memory location, which I mentioned holds the value of 5. So whenever it executes register 1 is equal to counter, register 1 will copy the value of 5 in it. That is denoted here. So value of register 1 is equal to 5. Now next instruction, which is part of again counter plus plus, is, see, this is the second instruction where we want to increment the value of register. So register 1 is equal to register 1 plus 1. So here what happens is value of register 1, which was loaded previously with 5, it becomes 6. And maybe before, which is counter is equal to, happen is maybe due to round robin or maybe any preemptive algorithm, scheduler activated and scheduler selected next process, that is the consumer, where consumer is executing the code counter minus minus, and counter minus minus is implemented as these three instructions. Okay, so whenever you are switching from one process to other process, your register values are stored somewhere, maybe in the process control block. That is what the context of this, right? So now consumer selected, and very first statement of that is register 2 equal to counter. Now what was the value of counter here? It is still 5. Value of counter is low 1, we have incremented 1, but we have not updated count. We have not updated that memory location. So it will still load the value of counter equal to 5. So value of register 2 is also 5. Now register 2 is equal to register 2 minus 1, because that is consumer. It is subtracting the counter. So it becomes 6. Sorry. Previously it was 2. It becomes 4. Fine. Now next statement is, suppose again producer selected by scheduling algorithm. So it will store at the memory location counter value of register 1, and value of register 1 was 6. So it will store the value 6 there. Producer is finished and consumer is selected. It will store the value of register 2 in the counter. which is again 4. So here, if you see initial value of count was or counter was say 5, initial value of counter was 5. Actually, what we did here is counter plus plus and counter minus. What I expect as a result is 5 only, right? But now it is giving wrong answer. It is giving 4. Now, if consumer has finished earlier than the producer, we get the value 6 because order we never know. Got it? Any doubt in this? Try to understand this one. Imagination is required here whenever we are actually switching from this to other. Fine. Now this is called as race condition. Both are trying to modify the memory location counter, okay, but this results into inconsistency. It is something like, for example, I have an account, and in my account I want to do some sort of operation like I want to withdraw 10,000 and I want to deposit 10,000. Maybe vice versa. You can. I just want to deposit 10,000. So my balance change. No, same thing is happening here. Count is incremented and once decremented. It should be its final value. That is not happening. Okay, this is wrong. This is wrong, and this is called as inconsistent state of data. Data inconsistency. Why this is happening is because of this condition. Okay. What I'll do is just a minute. Let me. I have a small program in. Let me check if it is available on this. Let me open. Now, we'll share this program with you. Let me. Is it visible? Is it visible? Okay. So let me explain what this program does is, actually, as I already mentioned, I'm using threads here. So multi-threading from C language, I already explained one example. Right? So this library we have used in this program. So pthread.h is the header file about rest of the thing. Now this is the routine or function which we call by the function. Okay, this is the function we want to call, and we know that with pthread underscore create we need to pass one function name. Okay, and who declaration should be void star. So return type is void star, and it will take only one parameter called as a void star. Right. So what I'm doing is now this is a counter, as just we are discussing about the in case of producer and consumer. Now here I am not working with producer and consumer. Let me remove this part. Right now it is not required. Let me make it simple. Fine. Now this is my main program, and one variable is there. Let us call it as a number of iterations. Okay, and I'm passing this number of iterations from command line argument. Okay, and I'm checking here. That means ARGV of 1, ARGV of 1. So by executing this program, for example, let me open, let me take it on right side. So it is something like this program is count.c. It is there, right? So let's save it here. First of all, how I want to execute is of compiling. Once I compile it, I want to execute this code something like this: a dot out, and I pass one number there. Say for example 5,000. Okay. With command line argument, this is argv of 0, and this is argv of 1. Getting it, no? I think you already studied command line arguments in the second year. So let us come back here. If you give that argument, this is just error in there. Number of arguments we need. One is name of the program, and second one is number of iterations. That is a number. Okay. And if you successfully give the second, now because this will be converted to long, ASCII to long. So data type of this iterations is long. Right. Now I just got some count, number 1. Number 2, initial stage of my counter is equal to 0. And now what I want to do in this code, that's the thread routine, is very simple. The number of iterations which we have taken from command line argument, they are passed as a parameter to thread. So count is name of my function, to which I am passing whatever the number of iterations. Say for example, it is 5,000. I am passing 5,000 here. So the same thing I am getting it here. And now whatever my global variable count is there, CNT. See, this is the global variable whose data type is long, right? So this global variable CNT will be incremented number of iteration times. So if previously it was like 0, and if I incremented 5,000 times, so CNT plus plus, this loop will be executed for 5,000 times. So once you finish, now what I'll do is, let us restrict ourselves to single thread. So let me comment out this one and this one. So just one thread I want to create here. Wait for completion of thread with pthread underscore join. And I just want to display the value of count. That's it. Okay. And for that, so what I'll do is, let me put comment for all this stuff. That is just to, anyways, I'll execute it with def value of count is equal to, this is long, so it should be LD, and let us display count. Even you can display the same here, even before creating the thread. So what I expect initially is definitely 0, right? So now I want to compile this program. So either use GCC or CLang, because I'm using threading part here. One more option, hyphen LP thread. Spelling mistake. Yes, and now execute it. So for example, same thing, 5,000. So initially I get count is equal to 0 before creating thread, and once thread is executed, count is incremented 5,000. So definitely I'm getting it to 5,000, right? Now, even you check it for any other count also, 1,000, 10,000, just 10, whatever. Definitely it will give you correct answer. But now there is a small modification. Here I want to do something like this. I'm calling the same function by two different threads, and now they are executing concurrently. Okay. And here I just want to display the count. Initial count I just removed because that is usually, right? Now tell me, let me first of all compile this code, and now I want to execute it with the count 5,000. Tell me what is the expected output. Anybody, please put on a chart. What is the expected output for the value of count? Yeah, somebody mentioned 10,000. Exactly. Why 10,000 is very simple thing, because the routine count is called by two different threads. One is by thread 1 with the number of iterations 5,000. Second time by thread number 2 again with the same count, that is 5,000, right? So the expected answer is 10,000. And now if you check, actually it is giving 8581. Okay, let me execute one more time. See, 10,000, 8730, 5136, 760. Every time I am getting something else, something different. Okay. Uh, if it is say 50,000, what I expect is 1 lakh. See, it is just giving me 59,705. This is what is called as inconsistent state of data inconsistency. Do you know why this is happening? Why this is happening is exactly same thing. Even though there is just CNT++, maybe this is being executed by thread 1 and by thread 2. Okay, and as I mentioned, let me stop sharing this. Exactly the same thing is happening there. Okay, so the variable count, now I just mentioned counter here, is being used by two threads simultaneously. That is the problem, and access to that is not provided in a proper way. This is called as rest condition. Remember, the net effect of this rest condition is data inconsistency. Any doubt in this? If you have any doubt, please put it on chat. Okay, fine. So I'll assume there is no doubt for this. Let us continue to our next slide, which actually try to put the problem of this race condition into a more technical problem called as critical section problem. Okay, and for this critical section problem, there is one assumption. Yes, we have n processes there. Like I just give an example of two threads or two processes. This can be extended to n more generically. So consider in my operating system there are n processes and they are denoted by p naught p1 up to p of n minus 1. Okay, so p0, p1, p2, p2, something like that. The names given to the processes for simplicity. Okay. Each process has critical section segment of code. Now we need to understand what is critical section segment of code. What is critical section segment of code? So in very simple words, I can say updating shared variable can be think as critical section. Okay. Now the same thing is mentioned. Process may be changing common. Now the word used here is common, but again the meaning of common is one which is shared between multiple processes. Okay, it may be changing the common variable, updating the table, writing file, etc. Okay, this is very important concept. Whenever process is dealing with, and this dealing is not just reading again, let me tell you, because if the data is being read by multiple processes concurrently, there is no effect at all. But whenever changing it, and this changing is what maybe we are modifying it, updating, writing, so different words can be used for that. So updation of 3-4 words are sufficient to mention what is the critical section. Okay, so whenever processes may be changing the common variables or updating some sort of tables or writing to files, etc. This code or this segment of code in every process is called as critical section. This is what the definition is. Okay. And one of the requirement of this is when one process is in its critical section, no other may be in critical section again. Okay, very simple and practical example I would like to give here is, assume that in a college LAN there is a single printer which is being shared between say 20 computers, and 20 users are there sitting on 20 different computers, and maybe one user has given some printout of a document which is in progress and that is not known to others. Okay, now what will happen if one document is being printed, another user also send a print. He is also trying to print another document. Now as we already aware, the resources are shared, but while sharing resources, what will happen, like it will print 4-5 lines from first document and 4-5 lines from second document. That is what the data inconsistency is. So there are resources, they should be used in proper way, and this proper way is exactly what we call as the serializable resource. Meaning of that is such resources should be used one after other. That means whenever one process is using it, no other is allowed to use it until someone releases that. Right? Same thing happens here. If there is a critical section, which is you can imagine like updation of shared variable. Like for example, whatever the program I just executed where we incremented the value of CNT by 1, CNT plus plus, that was the statement of the language. That is updation. And if one thread or one process is updating it, no other is allowed till previous operation is finished. So when one process is in critical section, no other processes are allowed to go inside the critical section. This is called as mutual exclusion. This is very, very important word. Mutual exclusion. That means at most one process is using that. At most I am saying. If no one is using it, no problem. That is absolutely no issue. But if somebody is using it, that count must be at the most one, not more than that. Okay. And providing solution to this critical section problem is actually like designing protocol to solve this. Okay. So the solution to the critical section problem is like, for example, we now need to design some sort of protocol so that so that we provide mechanism to avoid data inconsistency, right? That is what we want. And now then this solution to this critical section problem demands some sort of properties, and those properties are basically, I can say there are four conditions. So whatever the solution you want to provide for the critical section problem, that has to satisfy the four conditions. And these four conditions are: number one, which is the requirement at first of all, no two processes simultaneously go into the critical section. So this is very simple thing, like as I mentioned, rather than saying two or more, I can say. So at most one process should be in the critical region, or you can say critical section. And this property is, as I already mentioned, is called as mutual exclusion. Second thing is, whatever the solution you provide, it should not depend on the speed and the number of CPUs. Like one process is fast, running on fast processor, and another process is running on slow. And the process running on fast processor will get access to the critical section quickly. No, do not make assumptions about the speeds and even how many number of CPUs are there. That is the second bad property. Okay. Now, as I mentioned, if one process is in the critical section, definitely it will block another process who wishes to enter into the critical section. Now, that is as per requirement number one. That is fine. Absolutely no issue. But then the third requirement is, if one process is running outside of its critical section, I repeat, if process is running outside of its critical section, that process should not block another process. See, if one process is in critical section, that can block, absolutely no problem, because that is a requirement. But if one process is not in critical section. It is outside of the critical section. Such process do not have permission to block others. So your whatever algorithm is there, it should not block other processes if your process is not in critical section. Okay. And fourth condition that is required is regarding fair policy. If multiple processes wishes to enter into the critical section, everybody get chance to enter into the critical section. Otherwise, what will happen is like one process is always waiting for entering into a critical section and it is not getting. So that is that problem, I guess, we mentioned as a starvation. Okay, so every process should get chance to enter into the critical section, right? So looking at this, uh, for example, we know how railways are sharing the tracks. For example, from Kolhapur to Miras, there is a single track, assume, right? And maybe one railway want to move from Kolhapur to some destination via this track, and maybe other railways coming in reverse direction. So something like Goa to Kolhapur via Miras. But the thing is now this critical section now, right? Wherein we want to utilize single track, right? So what is solution for that? And the solution is something like before using the shared resource, process must ask for permission. Okay, so this is typically called as an entry section where before actually entering into the critical section, ask for the permission. If nobody is there, yes, permission will be granted to you. It is something like you acquired lock on that and then use it. And whenever you finish your critical section, you are supposed to release that lock. This section is called as a exit section. So total I can say four sections are there. One thing is entry section where you ask for the permission. Once you got the permission, if you don't receive permission, you are simply waiting here. You are repeating here. You are waiting here, here, here. Once you receive the lock, section number 2 is critical section. Once you finish using this critical section, now you release the lock. That is called as exit section. And other than critical section, your process is also doing some sort of other tasks. So we call that as a remainder section. Okay, this is remainder section. So typically we have the mixture of critical section and remainder section. But before entering into the critical section, we must go through the protocol called as entry section where we ask for the permission. If we get the permission, we execute critical section. Once we finish the critical section, exit section is required so that whatever the lock we acquired in the entry, we need to release that. Why? Otherwise, what will happen is I acquired lock, I used it, and I forget to release it. Others will be blocked. That is our requirement. If I am not in the critical section, so maybe I'm in the remainder of the section, because I have not released the lock, others are also blocked. That violates rule number 3. Okay, and this task is done repeatedly, so it is do while true. So it's infinite loop. So process is doing something like this. Okay. Any doubt? Any doubt? Yeah, somebody mentioned crossing on a station, and of course, token rings are used there in railways. Token rings, kind of locking system is there. Okay, fine. So we'll stop here today.